my screen? Can I get like a confirmation in the chat or something? Okay, audio's a little weird. Not sure if I can actually do anything about that though. Let's see. Is this a little bit better or not? Okay, if I have background noise, then we might have a problem. Yeah, my apologies. I don't think I can actually fix my mic issues right now, but am I at least, like, understandable? Okay, that's nice. Alright, so as Arvin said, I'll be going over the second problem for silver, which is test tubes. In this problem, Bessie basically has two test tubes, and each of the test tubes is filled with a certain combination of liquids. These liquids do not mix and they have different colors, which Bessie just calls colors 1 and 2. And these test tubes have infinite capacity, but in the beginning they're each filled with n units of some mixture of the two liquids. So since the liquids don't mix, once they settle, they divide into layers of like separate colors. So because of this, the two tubes can be viewed as strings, where like each index of the string is just a color of the tube. So Bessie wants to separate these liquids so that each tube contains contains like all units of a particular color of that liquid. And the way it works is that she can pour like every layer of a certain color of liquid into a different tube. And she also has a third beaker that's also infinite capacity that initially is empty. So your goal is just to figure out the minimum number of like pours it takes Bessie to like sort the colors into different tubes. And then at the very end, one of the tubes has to contain like all of one color and the other has to contain all of the other color. And then the beaker at the end also has to be empty. And you also have to construct the solution. You have to like figure out the exact sequence of moves. Obviously, in most cases, there are going to be multiple possible sequences, so outputting anyone is fine. Yeah, let's just jump into the solution right away. We are running a bit low on time. So a few basic observations for the sake of simplicity, it doesn't really matter how much of a color is like in a row in a tube, only like what color is at what positions in what order. So in other words, each tube is like actually functionally equivalent to either like 1 2 1 2 1 2 1 2 something or like 2 1 2 and 2 1 2 1 and blah blah. I'm gonna wipe my mic. Honestly, I doubt that's an option, but I will try. Any better? Okay, a lot better. Alright. So our goal now is to find a lower bound, and for the answer, simply to make our lives a lot easier when it comes to be greedy. So first of all, intuitively, the answer cannot be lower than the number of quote-unquote switches in the color in the test tubes. Whenever two opposite colors are adjacent, the top one has to be poured out, right? Like, let's say we have a 2 on top of a 1. We have to pour the 2 out because there's probably some 1 somewhere else that we have to pour into the 1, or if they like get the 2 into the other 2. Like, no matter what, if two colors of a liquid are in the same tube, we're going to have to pour one of them into the other because the tube can only have one color, right? So let's let the number of switches across both test tubes, like in total, like number of color switches called X, then the answer is at least X. If we do a little like just tinkering around, we can find that we can actually raise the lower bound a little bit. Let's consider the case to the right? Our test tube has size 2, and the first one is color 1 2, and the second is 2 1. So no matter what we do here, we can't actually get better than 3 moves. We're gonna have to move like one of them into the third test tube, no matter what. Like, even if there are only 2 switches, the answer is going to be 3, because let's just say we move the sequence like 1 3 and then 2 1 3 2. The 2 in the first test tube has to move into the third tube, and then and then it has to move back to the second tube later, so it takes 2 moves instead of 1. Ooh, my mic is wonky again. Yeah, honestly, I don't even know at this point. I apologize. So yeah, but like generally in this case, we can just extend this to all cases where there are at least 2 switches. Because if both like color switches are in the same tube, at least one color is gonna have to be part of the third tube, which would add a move. And if the 2 switches are in different tubes, like 1 switch in each tube, then it's just the case shown above. And obviously this applies to like if there are more than 2 switches as well. And then we can actually raise this lower down bound a little bit higher. Consider the following case, right? 2, 1, 1, and 1, 2. Even though there's only 1 switch, the answer is 3, which as you might know is actually 2 higher than the number of switches, not 1. And this is because not only do I have to move the 2 into the third beaker, but we also have to move one of the 1s into the other tube, right? We have to pour the bottom of the tube into the other tube, and we have to move something in the third tube and back. So again, this also just extends to any case where both test tubes have the same color at the bottom, because no matter what, the color at the bottom is going to have to be poured out, and there's going to be some color on the top that has to go into the third test tube, right? So to recap, if both test tubes share the same color at the bottom, the answer is at least x plus 2. And if they do not share the same bottom, but there are at least 2 switches, the answer is at least x plus 1. And if neither of these conditions are satisfied, the answer is at least x. Does that make sense? Alright, so now we're just gonna have to find a solution that actually meets these lower bounds, or at least very close to it. So the first thing to observe when we make the solution is that there's no point in dumping 2 different colors into the beaker, because that doesn't actually save you any moves under any circumstances. Because first of all, like let's say we dump 2 colors into the beaker, we're still gonna need 2 pours to move them both out. So we may as well just like pour the top color into like whatever tube it was supposed to be in, right? And if we pour 2 colors, it doesn't actually free up another like color underneath both the tubes to be poured either. Like if you do like a lot of playing around with test cases, you'll just realize that eventually, like, there's really no point in like freeing up 2 colors. Can I send the link for the slides? Yeah, no problem. Actually, can I do that afterwards? Like after I present? Yeah. So, yeah, as I was saying, it doesn't actually save you any moves to like dump 2 colors into the beaker. So no matter what, the beaker is only ever gonna have 1 color at one time. So we can just like, when we're sorting through the test tubes, we can greedily dump 1 color into the beaker and dump the other into the other test tube. Does that make sense? Yeah, alright, so just going like the way we construct a solution now. So like for sake of simplicity, we'll just assume that the first test tube has less switches than the second, and the bottom of the first test tube is color 1. If the top of test tube 2 is color 2, dump it into the beaker. And then now we go through test tube 1. If the top is color 1, dump it into tube 2. Otherwise, dump it into tube 3. And you don't dump out the bottom. And you do the same for test tube 2, right? If the top is color 1, dump it into tube 1. Otherwise, dump it into the beaker. If the bottom of test tube 2 is the same as the bottom of test tube 1, dump the bottom into test tube 1. Otherwise, just leave it there. And then at the end, just dump test tube 3 or like the beaker into tube 2. And then at the end, tube 1 is going to be all color 1 and tube 2 is going to be all color 2 and the beaker will be empty. So if we look at this algorithm carefully, it meets the lower bound for earlier, right? Because each switch, each color is dumped exactly once. And can't you only dump the top? Yeah, my meaning is basically you just take the tube one at a time. Like you go through each layer. If like the top layer is color 1, if the top layer is like color 1, we dump it into the other tube. If the top layer is color 2, then we dump it into the beaker. And then yes, this actually is going to be exactly the number of steps of the lower bound we calculated earlier, right? Because each layer from each tube is dumped exactly once. And if we put anything in the beaker, it's going to add 1, which is going to be the x plus 1 bound we got earlier from 2 switches. And if the tube 2 is of the same bottom, it's going to be +1 again. So that's going to be the x plus 2 bounds that we got earlier for having the same bottom. Does this make sense? All right, then I'll just hop into the implementation now. Then, all right. So here is the code in C++. Yeah. So at the beginning, we just take in the input, and then as we noted earlier in the slide, like we assumed without loss of generality that the first test tube was shorter and that the bottom of the first test tube was color 1. But like obviously when we're actually writing code, we're going to have to make sure that the test tube we're treating as first actually is the shorter one, and that the bottom and we actually do to like treat the colors differently depending on what the bottom of the shorter tube or the test tube 1 is. Yeah, so this is what we're doing here, right? While we're in the input, we're sort of like sorting the tubes. We don't care about multiple colors in a row, so we only like, I guess, like push it into our tube if it's actually a switch in color, right? So if tube A has less switches, then we treat it as the shorter tube, and otherwise what are A2 and B2? A2 and B2 are just like the character strings that are in there, and A and B is like the stack of things that I do. Because like, remember how I said it earlier, like we don't actually care how many like 1s or 2s are in a row. It's like functionally equivalent to like 1, 1 or 1, 2, right? So the stacks are just like 1, 2, 1, 2, 1, 2, or 2, 1, 2, and 2, 1, and the A2 and B2 are like the actual input value that they give you. Yeah. So I guess this is like the meat of the code here. This is our solve function. So A is going to be our shorter tube. It's going to be like our test tube 1 from earlier. And B is going to be our larger tube. It's going to be our test tube 2 from earlier. So AID is just like which tube the shorter one is, and BID is which tube the longer one is. It's just like make actually re-clean, please. All right. Any better? It's a little bit better, yeah. Okay, my bad. Alright, we are running a little low on time though, so I guess I'll just continue. Yeah. So back to the function. A is like our shorter stack, and B is our longer stack. AID and BID are like just there for constructing the solution. And bottom is the color of the bottom of the shorter tube, or tube 1. So our stack C here is just like what representing what's in the beaker at any moment, and our vector ops is just like the solution we're constructing. So first of all, at the very beginning, we're going to deal with the edge case where it's just 1, 1, and 1, 2 in like the 2 tubes, because our code actually does kind of crash there. So we're just going to take care of that test case immediately, and the answer is 0, obviously. Yeah, and then as we started, like, if test tube 2 is a different color from the bottom of test tube 1, then we dump it into test tube 3, or the beaker. And then we just go through test tube 1. If it's the same as the bottom of the test tube 1, then we just dump it into the other tube. Otherwise, we dump it into the beaker. And then we do the same for test tube 2. If it's equal to the bottom of test tube 1, then we'll dump it into the other tube. Otherwise, we'll dump it into the beaker. And at the end, if the bottom of test tube 2 is the same as the bottom of test tube 1, we just dump it into test tube 1. And then if we have stuff in our beaker, then we just dump it from the beaker into test tube 2. And then we just return our constructed solution. This is basically exactly what I explained earlier, yeah. So returning to the bottom here, yeah, so basically the way we call our solve function here is that if stack A, or like the first input, is shorter than like the second test tube that they give you, then we'll just plug it in as normal. Like A is the shorter tube, and B is the longer tube. But if B is like longer than if B is shorter than A, then we plug in like B as the shorter tube, and so on. And obviously like the bottom accordingly too. And yeah, and then we just output the answer. Does anybody have like any questions about the code? All right. If not, I'll just end it here, and then I guess if you have any questions, just slide it in the chat.
Okay, thank you. We do have a brief presentation from XCamp, if you want to start that. And then if you have any more questions, feel free to put that in the chat. And then our instructors will answer.
Yeah, so yeah, uh, yeah, so XCamp has like a USACO report. So basically you can write how many test cases you passed for each problem. And then you'll get like a report card emailed to you with some details. Yeah. Yeah, so it's still in development for the February version, but yeah, encourage people to use this for the January version. You can find a link here. Yeah. Yeah, that's all I had. Yeah, thank you.
Okay, thank you all for coming to the workshop again. And then that should be the end. Again, feel free to put any questions in chat, and thank you for coming.